So welcome. On today's PD lesson, we are going to solve this particular transport equation here, and you realize that with this transport equation, our speed here is not a constant but it's a variable. We have variables here, and we also have a non-homogeneous thing. So how do you go about solving this transport equation with this initial condition? So let's go through the solution. So you realize that our u here is a function of t and x. So that means that it's a multivariate function, but we would want it to be a function of just s. So to do that, we apply the chain rule. So using the chain rule, we are going to have du ds will be equal to this function that we have here, and you realize that with this particular function that we have here, this is the same as u of t and this is the same as u of x. So we end up with this. And when we make comparison with our question, you realize that that means that because d dt ds here is our coefficient of ut, so making comparisons, it means that the t ds is equal to 1 and the x ds is equal to xt. That's the coefficient of our ux. And the u ds will be equal to x squared. That's the non-homogeneous term. So we get this characteristic equation as I just explained. You realize that the initial condition was given as u of x0 equals 5x. There was no t component, so that means that our t of 0 will be equal to 0. And um, sorry. So we also have the u ds equal to x squared as we said. So solving the characteristic equations, this is the first characteristic equation. To realize that to solve it, we get the t will be equal to the s. So the t is equal to the s. Integrating both sides gives us t is equal to s plus c. When we put in our initial condition here, then we will get c to be 0. So t will be equal to s. So that's the solution from our first characteristic equation. Then we move on to our second characteristic equation. The x ds is equal to xt. But note that from our first characteristic equation, from the solution, t is equal to s. So that means in place of this t, we can put this s here. So now we end up with the x ds is equal to xs. Right? So now we have to solve for x. You realize that when you divide through by x, we get 1 over x ds will be equal to s ds. When integrating both sides, we know 1 over x. When we integrate it, we get ln x. This will give us s squared over 2 plus a certain arbitrary constant which we are calling x naught. So when you find the exponent on both sides, realize you get e ln x, then e power x square on 2, then dot e x naught. But I realize that since x naught is an arbitrary constant, that means e x naught is the same as x naught. So we still have our x naught here. And when you find the exponential of any line function, you get whatever is here. So we get this s. So we get s to be s naught e x square on 2. So when we decide to make s naught a subject, that means you have to divide through by e x square on 2, and we end up with this. But remember that our t is equal to s, so that means in place of the s we can use t. So that's what gives us this s naught equals x e minus t square on 2. We have solved our first characteristic equation and we've also solved our second characteristic equation. So now let's turn our attention to um the u ds equals x squared. So um realize that with the u ds equals x squared, we can decide to multiply through by ds, and when we do that, we are going to end up with du be equal to x squared ds. But remember that from the second solution, our x was equal to x naught e x squared on 2. I hope you remember. So from this place, from this place, that was our x. So we quote it here. Our x equal to x naught e squared on 2. And we have s squared here. So when you try to find s squared to square both sides, here we are going to end up with x naught squared e x squared. Right? So hence now the u which is equal to x squared d, instead of x squared, you put this there because that's the transformation we've done. Right? Then we integrate both sides. So when you integrate both sides, you get u which is a function of x and t, will be equal to integral from 0 to t, then x naught square e x square ds. So the integral of this from 0 to t, that's the limit. So you realize that our x naught here is a constant. So that means we can pull that one out because s naught is a constant. So when you put that one out, you get u be equal to s naught squared, then integral from 0 to t, es squared ds. But you should know that we can't use normal integration to do this, so we maintain it. But note that our x naught is equal to x e minus t squared on 2. That's from our solving our second characteristic equation. So when we square it, that means you're going to get the square of it to be this here. When you square this, you will get this. Alright. So now when you make substitution, instead of our x square, we put this one here. So we have u of xt will be equal to x squared e minus t squared and whatever is here. So you realize that this becomes our general solution where our e here is arbitrary, so an arbitrary constant. So now we have to put in our initial condition to find the e. So remember our initial condition was given as u of x0 equals phi of x. So when we put it inside our general solution here, we are going to get u of x0 will be equal to a phi of x naught. Remember that the reason we get a is that when you put x of 0 here, wherever we see t, you put 0 there. So here we are going to get from here, we are going to get integral from 0 to 0, which is going to make the whole of this 0. When you multiply through by 0, everything here will go away. So you'll be left with just a. So we get u of x0 will be equal to a. My initial condition was phi of x, and remember x is a function of t, so it will be x of 0, which is the same as x naught. So that's why we have phi of x naught here. So hence a is equal to phi of x naught. But remember from equation or solving our second characteristic equation that our x naught, so our x naught was equal to x e minus half t squared. So realize that when you put it through, then this becomes our a. So when you put our a through, then we get a particular solution for our transport equation as this. And you realize that use a function of x and t. Here we have s and ds here. You should know that we can't use normal integration to integrate this. That's why we left it. But I realize that because the limits are from 0 to t, even if you are supposed to integrate it, the s's are going to change from t. So u will entirely be a function of x and t. So this is the solution to the transport equation above, which had our c to be made up of variables and had a non-homogeneous term. I'm going to read our 10 days of mathematics. Thank you.